I have some late-breaking news for all of my subscribers. Did you know that the world's best statistical analysis software is actually available for free for students and educators? Yes, I said it right. Available for free. And it is called SAS. SAS. And if you ask anybody who knows anything about statistics in the real world, SAS is absolutely the industry standard. And most importantly, you can put this on your resume. I am going to show you how to get started with SAS by showing you a simple program to calculate relative risk. And since vaccine efficacy is nothing more than 1 minus the relative risk, I can frame this in a meaningful context, given that we are, as of this production, still suffering from a global pandemic where the role of vaccination is a central component of our scientific investigation. Come join me on this adventure. Once you register for SAS Studio as an individual learner through SAS for Academics, and you can see the description below, I'll shoot you to another YouTube video that actually comes from the SAS Institute. You will be able to have a window like this, and there's this little thing over here where you click and it will let you open up a new SAS program. I've already done this, and this is the window that you're presented with. Now, I already have a bunch of formulas, a bunch of folders. Here I have some basic stuff, but I want to take you through this process kind of from the beginning so you can see how to run a very simple program. So I'm going to run a whole new program. Now, the thing that you should know about SAS is that there are only two types of components to a SAS program. There are what's called data steps and there are what's called procedures. But nobody uses the word procedure. We use PROC for procedures. So I want to show you a very, very simple program first. So let's take a very simple hypothetical vaccine study. So let's call this data, and I'm going to call this D1. This is just the name of the data set. And I'm going to input some variables. So let's start off by assuming that we have a randomized, double-blind, placebo-controlled clinical trial, the best that our science has to offer. Something that, for example, Dr. Anthony Fauci loves. So let's just say we have two study arms. We have the vaccinees and we have the placebos. So what we're going to do is we're going to use an input statement. Now, I want you to notice when I type input, it comes in this color, this kind of blue color, which says that it is a recognized SAS word. And this nice little thing comes up. I didn't even have to put, like, as I'm typing this, INP. Now this is easy, UT, but I didn't even finish. I just put in the U, and it tells you right away that the statement is input. I double-clicked on it in case I didn't know how to spell input. Now, of course I do, but we have other things. Now, I'm having a variable called ARM for the arm of the study. Now, ARM is just really a fancy term for group, treatment group, but we call it ARM. And I'm making this a categorical variable. So I put a little $sign after ARM. In other words, it's not numerical. So if we have a categorical variable and, it's text but not numbers, you put a $sign after. Then I'm having a variable called HOSP, which is short for hospitalization. And I'm putting a $sign after this because it's going to be a yes-no variable. And I'm going to actually write YES, and I'm going to actually write NO instead of using like numbers like 0 and 1, 0 for no, 1 for yes. And then I'm going to make a variable called count. And these will be the number of hypothetical subjects that will go into this set of data. Now, when you're done with any kind of a statement in SAS, I want you to notice you have to use a semicolon that tells SAS we're done. Now the next, the next thing that you're going to do is tell SAS you're going to read some data that's hard-coded into the program. I'm just going to stick it right in the program, only because this is the easiest way to teach SAS. So the syntax is called cards, and this comes from, most people who are watching this don't even remember what punch cards were, but this is historical. So if you ever listen to one of the old Star Treks and you hear typing when you're saying, computer, can you please compute the trajectory to alpha, triangular, gamma 6, and you hear the typing. That's because in the old days they used punch cards, and SAS still uses this to tell the reader, to tell the compiler that data is going to come. So I'm going to put the data in now. So let's look at the vaccine arm of this study, and let's look at the people who are hospitalized. And let's look at the vaccine arm of the study, and let's look at the subjects who are not hospitalized. And then let's look at the placebo arm of the study who were hospitalized. And then let's look at the placebo arm of the study who were not hospitalized. So we have 4 groups. All right. Now, what I want to do is I want to put some numbers into this. And this is totally hypothetical, but I want to throw these numbers into it in a way where the math isn't super complicated. So let's make it as easy as possible. Let's make it 50-50. So in other words, let's say we had 100 study subjects that were randomly assigned to receive the vaccination. And out of these 100 subjects, 50 ended up being hospitalized and 50 ended up not being hospitalized. Okay, I'm just trying to make the numbers as simple as possible so we can talk about it. But let's have that. And then let's look at the placebo. Let's look at the study subjects who were randomly assigned to the placebo. And let's just say, I don't know, make it 60-40. 60-40. Okay, so we have 60 subjects who were randomly assigned the placebo who ended up getting hospitalized. And we had 40 subjects who got the placebo who ended up not being hospitalized. And so this is about as simple a data set as you could probably ever have. But, when you teach, you want to go with the simplest possible. So then you have to tell SAS that you've finished entering the data. So you type the word run, and then semicolon, right? Okay. So now let's check just to make sure I didn't make any kind of mistake. So what I like to do is I like to look at my data. So I go proc print, semicolon, and then run, semicolon. And I see I put the extra P. You know what? I'm going to leave the extra P because I want to show you what happens when you run it. I think that's a good thing. So this will just print up the data. So see this little icon of a cartoon character running. This is how you run the program. So I know there's going to be an error because I put 2 P's, but I just want you to see what happens. So we run it. Strangely, I expected to get an error from the 2 P's. I didn't, because you actually got the 50-50 and the 60-40. But I'm going to fix it anyway. So I'm going back to code because, I can't leave it this way. It's wrong, So I'm going to put it back. I'm going to run it again. Let's see what we got. Notice the table looks a little nicer, right? We got our 50-50. We have our 60-40. Looks like it's good. I'm not going to keep this proc print just because, well, you know what? Maybe I will. I'll leave it there. Okay, so the next thing I want to do is I told you that I was going to show you how to compute relative risk and how to compute a confidence interval for the relative risk, because 1 minus the relative risk is the vaccine efficacy, and 1 minus the bounds of the confidence interval for relative risk gives you the confidence interval for vaccine efficacy. Is that not amazingly cool or what? So here's how we're going to do it. We're going to use a procedure called frequency. So it's proc and it's freq, FR. Now, do you notice how I didn't even have to type it? It gives me choices. I just double click. Doot. Is that cool or what? Now, I'm going to use an option, and I will explain to you, you know what, maybe I won't use the option. I'll just do it this way, and then I'll put the option, and I'll show you what I'm going to do. So let's do proc freq, and we're going to want to see a table, right? So let's do this. Let's go table, and we want the arm of the study, and then we use an asterisk. This means by, and then whether or not the study subject was hospitalized, right? And I want to perform a basic chi-square test. Now, I have enough data to perform a chi-square test. I can look at this, and I know the expected frequencies are greater than or equal to 5, and I know that's going to be fine for, validly interpreting the chi-square test statistic. I know that. But sometimes when I'm teaching in class, I like to ask some questions. Show of hands. Who thinks this? Who thinks that? We get one of these 2x2 classification tables, and we don't have enough data to do a chi-square test. So I use, now see, I just typed FIS, and see how this comes out? Click on it, Fisher. What this does is this tells SAS that if you don't have enough study subjects to have expected frequencies of at least 5, it uses Fisher's exact test. And if you did this by hand, oh my God, it would be a nightmare. But SAS just does it for you. Now, with this amount of study subjects, it's not going to do Fisher's exact test. It's going to do the chi-square test. But if we only had a few study subjects, it would do Fisher's exact test. The next thing I want to do is I want to put relative risk in here. Now, notice all I did was type the letter R. I didn't even have to type relative risk. It's right here. Double click, semicolon. Okay, we're almost there. The next thing I want to do is I want to do what's called weighting. So WEI. Now notice I was about to type in weight, but I may not have forgotten, the I before E except after C thing. That doesn't always work. I don't know. Maybe I couldn't spell it right. It fills it. Double click, weight. And how am I weighting this? By this count variable, COUNT, right? Now, when you're done with a procedure, you always have to type run semicolon. Okay. Now, there's going to be a little problem with this. I know it, but I want to show you what the problem is so that I can show you how incredibly easy it is to fix this on SAS. So, I don't think I want to bother. I'm going to get rid of this proc print just because I want it easy for you guys to see, for you all to see. So I'm going to click the icon of the running person. And here we have a table of the study arm by hospitalized. Now here's the problem. Nobody puts placebo first. You always put the experimental group first, and nobody puts the no first. SAS is doing that because SAS wants you, I'm only guessing why, but I think SAS wants you to be sure what you're doing so that you don't mess things up. So SAS wants you fully invested in every aspect of this. So the way we're going to get the vax over here and the placebo over here, which is how you have to do it in the real world, and you never put the no before yes. You're interested in the yes. You're not interested in the no. You always define yes to be that thing that you're interested in. You're interested in whether a patient has to end up going to the hospital. So the yes has to go over here. So the way I'm going to fix that is I'm going to go back into the code, and I'm going to go back into proc freq. and I'm going to put what SAS calls an option. And the option is order. Now notice I just put an O and it comes right here. And I click, and I'm going to click on data. Order equals data. Now I'm going to run this and check what we get. Now we get it exactly the way we would need this table in the real world. Experimental group comes first, control group comes second. The yes category comes first, the no category comes second. And now we have our nice little table. Now I want you to notice that this is the data. Again, we wanted the vaccinated group to be 50-50 because it's just so easy to do mathematically. And we wanted the placebo group to be 60-40. So there's a little bit more chance that an individual given the placebo would end up in the hospitalized group. This is all hypothetical data. I'm just illustrating something. Okay. So take a little look at this. Now, the next thing I want to do is I want to look at the chi-square p-value, and that's right here. Now, if you haven't watched any of my videos on p-value, and you don't know what a p-value is yet, well, you're going to want to watch my videos on hypothesis testing and p-value. I'm not going to go into that in great detail, but in the real world, the world of science that, our current culture embraces, the significance level that we perform hypothesis tests under by default is 5%. So this is almost a 16% p-value. And the decision rule is that if the p-value is less than or equal to the culturally accepted significance level of 5%, we reject the null hypothesis of no association. And here we can even test for a causal relationship because I said it was a randomized, double-blind, placebo-controlled clinical trial. So we can even test whether vaccination causes less hospitalization because of the randomization. Now, unfortunately, with this p-value, it's not statistically significant. 15% p-value? Sorry. No go. But I want to show you a little something since this is a stats class. And I'm going to show you actually, before I show you, you know what I'm going to show you now? I'm going to show you something. I want to show you what happens. Let's change these 50s to 500s. So now instead of having 100 study subjects per group, now we have 1,000. Right? Just multiplied everything by 10. See, 500 plus 500 is 1,000, so 1,000 people were vaccinated. 600 plus 400 is 1,000, so 1,000 study subjects were randomly assigned to the placebo group. Let's see what happens to the p-value. Check this out. Same relationship of the data, but now the p-value is highly significant. The reason for that has to do with statistical power. I'm not going to get into that in this video. If you know what statistical power is, you'll be like, oh, that's so cool. SAS showed that so easily. But if you don't know what statistical power is, do a little reading into it, and you'll see the role of sample size in statistical power. But I want to go back and I want to change this to the original data because it's easier to work with 100 than it is with 1,000. I mean, for the average, person. So I want to go back. Now, I want to talk about relative risk. Now, I have a whole video series on relative risk. And if you don't know it, it might not be the worst thing to review it before continuing, but I'll give you a really quick summary of what this statistic means. Relative risk would be estimated from these data as the probability of randomly selecting a study subject who was hospitalized, given that they were vaccinated, divided by the same probability that they were hospitalized, given that they were they were randomly assigned to the placebo. Now, before we even look at the output, I want to show you how easy it is to get relative risk. So I'm just going to go get my cell phone so I can ask Siri to do a calculation in front of you. Okay, I have my cell phone here. So let's get the probability so let's divide these two probabilities. Now I picked this 50-50. So the probability of randomly selecting a study subject who was hospitalized, given that they were vaccinated, is 50-50, or 0.5. That's the probability, 0.5. 50-50 is 0.5, 50% chance, right? Because the total is 100, right? So 50 over the total of 100 is 0.5. Right? The probability of randomly selecting a study subject who was hospitalized, given that they were randomly assigned the placebo, 60-40, the probability is 60 divided by 100, which is 0.6. So listen to this carefully. Hey Siri, what is 0.5 divided by 0.6?
0.5 divided by 0.6 is about 0.8333.
All right, so you heard it here first, 0.8333. Let's see what happens when we run this code. And now let me scroll down a little bit. And do you see the relative risk here is 0.8333? Now, you always use column 1. If you format the table correctly, you use column 1. And when I say format the table correctly, I mean the experimental group comes first, the placebo group comes, the control group comes second, the yes comes first, and the no comes second. So if the table is formatted correctly, you use relative risk column 1, which, as Siri told us, was 0.8333. That means, check this out. Hey Siri, what is 100 minus point, I'm sorry, wait.
Okay, I found this on the web from...
Sorry, I said that wrong. Hey Siri, what is 100 minus 83.33?
100 minus 83.33 is 16.67.
That means the vaccine efficacy was estimated to be 16.67%, right? That's how you compute vaccine efficacy. It's nothing more than 1 minus the relative risk. So it's about 17% is your vaccine efficacy. Now, 17% is garbage, you know, but I just wanted to illustrate it. Not only is it garbage, but you could see that this is not significantly different from 1. Now, if you watched my videos on relative risk and odds ratio, you know that the null hypothesis would be that the relative risk is equal to 1. And the reason why that is because if a numerator is equal to the denominator, then the fraction is equal to 1. So if there's no difference in the vaccinated individuals versus the placebos, that would mean the numerator is the same as the denominator. And that would be 1. So here, this confidence interval, 0.6, I don't know, let's say 5 to 1.07, you'll see that these bounds capture that number of 1, which is hypothesized under the null hypothesis of no difference, no effect. So we already knew that this was a non-significant association due to this chi-square value. So we knew that. But this is also a non-significant association because the confidence limits for the relative risk, column 1, is from 0.647 to 1.073, which captures that number 1. So this is non-significant, either way you slice it. Now, remember I told you vaccine efficacy was 1 minus the relative risk. So the relative risk of 1 minus 1 is 0. So the null hypothesis is that there is no vaccine efficacy. That is, the vaccine efficacy is a big fat 0%. Okay, well, we know that the vaccine efficacy is estimated to be 1 minus 0.8333, and as a percent, it's about 17%. But it's not statistically significant. Let's go back to the code. Again, let's change these to 500s. Oh, put the 0 in the wrong place. That would have been an error. Change this to 600. Change this to 400. All right. Now we have 1,000 subjects per arm instead of 100. We're going to run it again. And we already know that, the p-value is incredibly small, which means highly significant. But now look at the bounds of the odds ratio. Look at the bounds of the relative risk. We still have the same 0.8333. We haven't changed the ratio of these two conditional probabilities. That's the same. We still have the crappy 17% vaccine efficacy. We still have a relative risk of 0.83 or 83%. But now look at the bounds of the confidence interval. Both bounds are less than 1 for the relative risk, column 1. So since both bounds of the 95% confidence interval for the relative risk are less than 1, that means 1 minus both of these bounds are going to be greater than 0. Now again, 1 is the hypothesized value under the null hypothesis of no causal relationship between study arm and hospitalization, using the relative risk as the measure of interest. If we use vaccine efficacy, which is 1 minus the relative risk, let me show you how we would do this kind of step by step. So this here is the point estimate for relative risk, right? This is the lower bound of the confidence interval, right? And this here is the upper bound. For the confidence interval for relative risk. So now let's look at vaccine efficacy, right? So, I put that in the wrong place. It's not easy doing this on the fly on Microsoft Word, but my viewers are worth it. Vaccine efficacy Hey Siri, what is 1 minus 0.8333?
1 minus 0.8333 is 0.1667.
Hey Siri, what is 1 minus 0.7693?
1 minus 0.7693 is 0.2307.
Hey Siri, what is 1 minus 0.9028?
1 minus 0.9028 is 0.0972.
So if we express this as a percentage, this is about 23%. And this is about 9.7%. I'd say 10%, just to round it off. But you know what? I'm going to leave it as 9.7%, just so there's no confusion. Now, I want you to notice here that 23% is greater than 9.7%. So even though this is the lower bound for the confidence interval for the relative risk, now This is actually the upper bound. Upper bound for the confidence interval for vaccine efficacy. And this is now the lower bound and this is what we, over here, this is what's called the point estimate for the vaccine efficacy. Okay, so let's look at what we've done here, right? So the relative risk is the relative risk for hospitalization, vaccinated versus placebo, is 0.8333, which is about 83%. The vaccine efficacy is about 17%, because it's 1 minus the relative risk. I should have made a table, but anyway, so I want you to see that here the lower bound is to the left and the upper bound is to the right, but when we do 1 minus, it's going to be in the opposite direction. So let's just kind of summarize this. So if we wanted to write this in standard written English, we might say vaccine efficacy was observed to be 16.67%, 95% CI colon, 9.7% to 23%. Notice that both bounds of the confidence interval for vaccine efficacy are greater than 0. Period. This means that the vaccine efficacy is significantly greater than 0. Period. But I want you guys to see, I'm not going to put it in the writing on Microsoft Word, but I want you to see here that it's still crap because even accounting for chance, this vaccine efficacy won't go above 23%. This is crap, but it's significant crap. So what I want to show you readers in, well, you viewers in YouTube land, is that you can have a statistically significant vaccine efficacy, but it's still clinically crap, right? Because it doesn't, you know, accounting for chance. The best you're going to get is 23% at the default level of significance in our scientific culture. That's terrible, but still statistically significant. If you watched this whole video, thank you for watching.